This training module titled Green-Blue Infrastructure for Flood Control introduces the conceptual and practical framework of green-blue infrastructure as a nature-based strategy for managing urban flood risks. Developed within the EPD-Net project, it highlights the integration of ecological planning and design approaches to enhance disaster resilience and support the development of sustainable cities. This slide outlines 3 key learning objectives. First, Green-Blue Infrastructure, GBI, is defined, with emphasis on its functions in flood mitigation. The conceptual foundations and core mechanisms are introduced within the context of urban resilience. Second, key design elements and systems for urban water management are identified. The integration of nature-based and engineered approaches is discussed in relation to contemporary flood control strategies. Third, the broader co-benefits of GBI are examined, including urban cooling, habitat provision, and recreational value, highlighting its multifunctional role in sustainable urban development. This slide introduces Green-Blue Infrastructure, GBI, as a holistic approach to urban water management. GBI deliberately integrates vegetated systems, green, with water-related features and management systems, blue. Instead of treating stormwater as waste to be rapidly conveyed away, this approach works with natural hydrological processes to slow, store, filter, and absorb water within the urban landscape. It represents a shift from conventional grey infrastructure, such as pipes and concrete channels, toward nature-based solutions that mimic ecological functions. The green component includes trees, shrubs, grasses, and wetland vegetation, as well as green roofs, bioswales, vegetated swales, urban forests, street tree canopies, community gardens, and parks designed with infiltration capacity. The blue component consists of rivers, streams, and restored floodplains, along with retention ponds, urban canals, constructed wetlands, permeable surfaces that enable groundwater recharge, and rainwater capture and harvesting systems. Together, these integrated systems enhance natural infiltration, reduce peak runoff volumes, improve water quality, and generate long-term ecological and social value within urban environments. For much of the 20th century, urban water management was shaped by a convey and remove philosophy. Stormwater was treated as a problem to be eliminated quickly through pipes and drainage systems. This led to the widespread construction of underground networks, concrete-lined channels, and engineered levees. Although effective in certain contexts, conventional grey infrastructure presents important limitations: high construction and maintenance costs, limited flexibility, and the absence of ecological or social co-benefits. The grey infrastructure approach rapidly conveys water away from urban surfaces and relies heavily on pipes, concrete channels, and underground storage tanks. Its capacity is fixed at the time of construction, making adaptation to changing climate conditions difficult. In addition, it contributes little to urban quality of life and may intensify the heat island effect. In contrast, the green-blue infrastructure approach manages water at its source. It slows, stores, infiltrates, and treats runoff through the use of vegetation, soil systems, and integrated water features. Life cycle costs are often lower when long-term environmental and social benefits are considered. Beyond flood control, this approach delivers cooling effects, biodiversity enhancement, recreational opportunities, and well-being benefits. It is also adaptable, scalable, and suitable for retrofitting within existing urban areas. The most resilient and effective urban water management strategies integrate elements of both approaches, combining engineered reliability with nature-based multifunctionality. While flood risk reduction is the primary driver for GBI investment, it is important to emphasize that the ecological co-benefits of well-designed systems are substantial. Municipal governments increasingly recognize these additional benefits as central to the overall business case for GBI. These benefits extend across multiple urban systems, from public health and thermal comfort to biodiversity and urban food systems, which makes GBI one of the most multifunctional infrastructure investments available to cities today. Looking first at urban heat island mitigation, vegetation and open water surfaces reduce ambient temperatures through evapotranspiration and shading. Research indicates that GBI can reduce local surface temperatures by 2 to 8 degrees Celsius, which significantly lowers heat-related health risks and decreases energy consumption for cooling. In terms of biodiversity and habitat, connected green-blue corridors function as ecological stepping stones. They enable the movement of birds, invertebrates, and small mammals across otherwise fragmented urban landscapes. Native planting within GBI systems also supports pollinators that are critical to urban food systems. Regarding air quality improvement, vegetation in GBI systems captures particulate matter, absorbs gaseous pollutants such as nitrogen dioxide and ozone, and produces oxygen. This contributes to measurable improvements in urban air quality, particularly along high-traffic corridors. Finally, community health and well-being outcomes are consistently linked to access to green-blue spaces. Evidence shows improvements in mental health, increased physical activity, and stronger social cohesion. In this way, GBI infrastructure creates public amenities that serve diverse urban communities across all demographic groups. A well-designed GBI system relies on a diverse toolkit of landscape and engineering elements. Each element performs a distinct yet complementary function in managing urban water flows. These interventions can be implemented at multiple spatial scales, from individual buildings and parcels to neighborhood, city, and watershed levels. Their effectiveness increases significantly when they are planned and connected as part of an integrated urban network rather than as isolated measures. This toolkit includes bioswales, rain gardens, and constructed wetlands, which slow, filter, and retain stormwater close to its source. Green roofs and permeable pavements contribute to on-site infiltration and reduce surface runoff in densely built areas. Floodable parks and river restoration projects create space for water during peak events while enhancing ecological quality. Blue-green corridors and urban canals strengthen hydrological connectivity across the city and support both environmental performance and public amenity. Together, these design elements form a flexible and scalable framework for sustainable urban water management. In this slide, the focus is on two key GBI design elements: bioswales and rain gardens, along with constructed wetlands. Bioswales and rain gardens can be understood as shallow, vegetated channels or bowl-shaped depressions. They are specifically designed to slow down, filter, and infiltrate stormwater runoff coming from roads, rooftops, and other impervious surfaces. In practice, they are considered among the most cost-effective GBI solutions, particularly in retrofit applications within existing urban neighborhoods where space and budgets may be limited. Constructed wetlands, on the other hand, are engineered shallow water systems planted with emergent vegetation. Their primary function is water quality treatment. They remove nutrients, sediments, and pollutants from stormwater runoff before it enters receiving water bodies. At the same time, they provide significant habitat value for birds, amphibians, and invertebrates. In this way, they not only contribute to stormwater management but also actively strengthen urban biodiversity. In this slide, the focus is on two key GBI design elements: bioswales and rain gardens, along with constructed wetlands. Bioswales and rain gardens can be understood as shallow, vegetated channels or bowl-shaped depressions. They are specifically designed to slow down, filter, and infiltrate stormwater runoff coming from roads, rooftops, and other impervious surfaces. In practice, they are considered among the most cost-effective GBI solutions, particularly in retrofit applications within existing urban neighborhoods where space and budgets may be limited. Constructed wetlands, on the other hand, are engineered shallow water systems planted with emergent vegetation. Their primary function is water quality treatment. They remove nutrients, sediments, and pollutants from stormwater runoff before it enters receiving water bodies. At the same time, they provide significant habitat value for birds, amphibians, and invertebrates. In this way, they not only contribute to stormwater management but also actively strengthen urban biodiversity. In this slide, the focus is on two key GBI design elements: bioswales and rain gardens, along with constructed wetlands. Bioswales and rain gardens can be understood as shallow, vegetated channels or bowl-shaped depressions. They are specifically designed to slow down, filter, and infiltrate stormwater runoff coming from roads, rooftops, and other impervious surfaces. In practice, they are considered among the most cost-effective GBI solutions, particularly in retrofit applications within existing urban neighborhoods where space and budgets may be limited. Constructed wetlands, on the other hand, are engineered shallow water systems planted with emergent vegetation. Their primary function is water quality treatment. They remove nutrients, sediments, and pollutants from stormwater runoff before it enters receiving water bodies. At the same time, they provide significant habitat value for birds, amphibians, and invertebrates. In this way, they not only contribute to stormwater management but also actively strengthen urban biodiversity. In this slide, the focus is on floodable parks and river restoration as strategic components of green-blue infrastructure. Floodable parks are designed as multifunctional landscapes. Under normal conditions, they operate as recreational spaces used for walking, sports, and community activities. However, during peak rainfall events, these same areas temporarily store excess floodwaters. This reduces pressure on drainage systems and lowers downstream flood risk. Once water levels recede, the space drains and returns to everyday public use. In this way, a single intervention serves both hydraulic and social functions. River restoration complements this approach by renaturalizing altered or channelized waterways. Restored rivers reconnect with their floodplains, improve ecological health, and enhance overall hydraulic performance. Blue-green corridors then link these GBI design elements together. By connecting parks, waterways, and green spaces into continuous networks, they support integrated water management while also enabling biodiversity movement. At the urban scale, this networked approach significantly strengthens resilience and environmental performance. The sponge city concept originates in China and has since been adopted internationally as a strategic planning framework for urban water management. It provides both a conceptual metaphor and a practical model for implementing green-blue infrastructure at the city scale. The core idea is that cities should function like sponges, absorbing, storing, purifying, and gradually releasing stormwater, instead of immediately channeling it into drainage networks. This framework is organized around 4 key processes. First, absorb. Permeable surfaces, green roofs, and rain gardens capture rainfall at the source, reducing rapid surface runoff and relieving pressure on drainage systems. Second, store. Retention ponds, wetlands, and subsurface storage systems temporarily hold water. This attenuates peak flows and allows water to be released in a controlled manner. Third, purify. Vegetation, soil layers, and microbial processes filter pollutants, nutrients, and sediments from stormwater before it is discharged or reused. In this slide, the focus shifts specifically to the benefits of green-blue infrastructure for flood control. First, in terms of stormwater management, GBI slows runoff velocity. By reducing the speed and volume of surface water, it lowers the risk of combined sewer overflows and flash flooding, particularly in low-lying urban districts during intense rainfall events. Instead of overwhelming sewer systems, water is retained and managed closer to where it falls. Second, regarding groundwater recharge, GBI increases infiltration across impervious urban surfaces. This helps restore groundwater levels and supports long-term water security. This function becomes especially important in regions that experience periodic drought conditions. Third, in relation to water quality and biodiversity, GBI systems filter pollutants, excess nutrients, and sediments from runoff before they reach receiving water bodies. At the same time, they create habitat corridors that support urban wildlife and pollinators, strengthening ecological networks within the city. Finally, cooling and well-being benefits should not be overlooked. Through evapotranspiration and shading, green-blue systems reduce urban heat island effects. In addition, they provide accessible green spaces that promote mental health, physical activity, and social cohesion. Taken together, these benefits demonstrate that GBI is not only a flood control strategy, but a multifunctional urban resilience investment. Let us now examine a real-world example of green-blue infrastructure in practice: Chulalongkorn University Centenary Park in Bangkok. Bangkok is a low-lying city that faces significant flood risk due to intense monsoon rainfall, rapid urbanization, and limited natural drainage capacity. Instead of relying solely on conventional drainage systems, this park was designed as a large-scale nature-based solution for urban flood resilience. The park covers approximately 11 hectares and incorporates a carefully engineered topographic slope. This sloped landscape is intentional. It allows rainwater to flow gradually from the higher end of the park toward a large retention basin at the lower end. As stormwater moves through the site, it follows the sponge city logic. It is absorbed by permeable surfaces and vegetated areas, it is stored temporarily within rain gardens and detention areas, it is purified through soil and plant-based filtration systems, and finally, it is released or reused in a controlled manner. The park can store up to approximately 1 million gallons of stormwater during heavy rainfall events. This significantly reduces pressure on Bangkok's drainage infrastructure and mitigates flood risk in surrounding districts. Beyond flood control, the project delivers multiple co-benefits. It reduces urban heat through evapotranspiration, improves biodiversity, and provides recreational and social space for students and the wider community. Chulalongkorn Centenary Park demonstrates that green-blue infrastructure is not merely a technical drainage solution. It is an integrated urban design strategy that combines engineering performance, ecological restoration, and public space creation in a single multifunctional landscape. The Sivas Kazilimak River project adopts a terrain-sensitive watershed planning framework by integrating spatial datasets related to elevation, hydrological soil groups, permeability, erosion susceptibility, and land cover characteristics. Through the identification of hydrologically functional planning units, the project explores the relationship between slope conditions, runoff potential, and land use patterns within the Kazilimak River basin. Although the project focuses on a river corridor, its methodological approach is grounded at the micro-watershed scale. Accordingly, the ecological connectivity between the project corridor and the broader watershed system has been examined to assess the extent to which the corridor functions as an integrated component of the larger hydrological and ecological network. Design interventions are developed in response to topographic constraints and surface flow regimes, prioritizing infiltration-supportive land uses in low-gradient zones and runoff control strategies in steeper terrain segments. The integration of riparian buffers and interconnected green infrastructure systems enhances hydro-ecological continuity while mitigating localized flood risks and soil erosion. These terrain-responsive design measures further support microclimatic stabilization by increasing surface permeability and evapotranspiration potential across the watershed landscape. To conclude, this slide summarizes the key takeaways from the discussion on green-blue infrastructure. First, green-blue infrastructure can be understood as a nature-based solution for resilient flood management. Rather than relying solely on conventional gray systems, it works with natural processes to manage stormwater at its source, reduce peak flows, and restore elements of the natural water cycle within urban environments. Second, GBI represents a meaningful integration of engineering and ecology. Effective implementation requires interdisciplinary collaboration, bringing together hydrological engineering, landscape architecture, ecology, and urban planning into cohesive, context-sensitive designs. Finally, GBI delivers multiple benefits across urban systems. Beyond flood control, it contributes to urban cooling, biodiversity enhancement, improved water quality, public health, and recreational opportunities. For this reason, it should be viewed not only as drainage infrastructure, but as a high-value investment in long-term urban resilience and sustainability.